Easy to apply, fairly easy to interpret, commonly utilized, readable, understandable, impactful, and useful. These are the adjectives and terms which I would utilize to describe the Pearson product moment correlation. The Pearson product moment correlation, also known as the Pearson correlation, is what will be discussed in this lecture. All examples will be presented within RStudio, with output reported within the APA results format. All code and data can be found in the video description below. Data is in CSV format. The Pearson product moment correlation coefficient, or Pearson Correlation Coefficient for short, is a measure of the strength of a linear association between two variables and is denoted by R. Model assumptions. The two variables should be measured on a continuous scale. The two continuous variables should be paired one-to-one. There should be independence of cases. There should be a linear relationship between your two continuous variables. Theoretically, both continuous variables should follow a bivariate normal distribution. There should be no univariate or multivariate outliers. How can we determine the strength of association based on the Pearson correlation coefficient? The stronger the association of the two variables, the closer the Pearson correlation coefficient, R, will be to either +1 or -1, depending on whether the relationship is positive or negative, respectively. Achieving a value of +1 or -1 means that all of your data points are included on the line of best fit. There are no data points that show any variation away from this line. Values for R between +1 and -1, for example, R equals 0.8 or -0.4, indicate that there is variation around the line of best fit. The closer the value of R to 0, the greater the variation around the line of best fit. So here are some diagrams of relationship directionality. For R equals 0.7 and R equals 0.3, these relationships have a positive correlation. An increase in X should also correspond with an increase in Y. Here we have a negative correlation in these two diagrams. R in this case is -0.7 and R in this case is -0.3. Here we have an increase in X corresponding with a decrease in Y. Increase in X, decrease in Y. In this case, there is an inverse relationship. Are there guidelines to interpreting Pearson correlation coefficient? Yes. If you took a look at this particular table here, we could determine the strength of association and whether or not the correlation is positive or negative as it relates to its value of R. So in this case, if our R value is 0.1 to 0.3, we have a small positive correlation. If we have an R value of 0.3 to 0.5, we have a medium positive correlation. -1 to -0.3, that's a small negative correlation. And -0.3 to -0.5, that's a medium negative correlation. And that's all dependent on what the R value is. So there's no easy way to, unfortunately, perform this analysis in R Commander. So we're going to be performing R analysis in R or RStudio, whatever you would prefer to utilize. Here is the code that would be necessary. If our data is in an Excel workbook, we would have to come up with a name of our data set as we'd like to utilize in R. We would utilize then the function readXL. Here's our file pathway. And finally, after this last slash, we have the name of our file, our Excel file, .xlsx, or whatever the extension is for your Excel file. Row names equals false is indicating that there are no row names in the first column of data. Header equals true is indicating that the first row, as we go across the top and go to those particular columns, that is indicating that the first entry in each column is the name of the corresponding variable. Sheet equals sheet1 is informing R that we want to use the first sheet of our Excel workbook. That's what we'd like to import. Maybe we have data on multiple sheets of the workbook, but we're only interested in importing the first sheet, and just leave stringsAsFactors equals true. Here we're also naming our dataset. In this case, we're using the function read.table. This is the file pathway, and our data is here with a .csv extension. Fill equals true is informing R that our observation sizes differ, which means we may have more observations in one variable than another. It's best to always keep this equal to true. Header equals true is informing R, just as it was in this case, that the top row within the data that we are importing, the top row corresponds to variable names. And sep equals, in quotations, comma, is telling R that we're working with a comma-separated value. Our data is separated by commas. And this data that we're going to be working with is in a comma-separated format, and it's in the video description below, along with all of this code. So here is what the code would look like in our studio, or R, not our commander. This is our data frame. And we're going to name this particular set as it exists in R. We're going to name it just Dataset. So we imported our dataset as either a CSV, from a CSV or an Excel file, and we named it Dataset. Okay, so our dataset's named Dataset, easy enough. Something you should remember is the names of both variables and datasets are case sensitive in R. In any event, our dataset has two variables, X and Y. And because we left our header equals true, that informed R when we were importing our data that this row here, X and Y, that is the name of our variables in our data set. You're going to need to have these particular package libraries already downloaded and installed in R or RStudio, those being ggpub-r and T-series. So it's two separate downloads and installations. Once you have those downloaded and installed, you can then initiate them with library function ggpub-r and library function T-series. Now, for APA format, we're going to need the mean of variable X and the mean of variable Y, the standard deviation of variable X and the standard deviation of variable Y. And we're going to get those values from our data set, which we've named dataset. Now, if our data set was named, I don't know, dataset A or pencil or fishbowl, instead of dataset, that would be the name. So if our dataset was named dataset A, this would be dataset A. If it was named pencil, it would be pencil. If it was fishbowl, this would be fishbowl. Dollar, the dollar sign, that's referring to the variable within the dataset. So our dataset's named dataset, and our variable is named X. If this was named var1, it would be dataset $var1. If our variable was named var1 and our dataset was named pencil, it would be pencil $var1. Okay? So mean, name of the dataset, dollar sign, name of the variable within the dataset. Standard deviation, SD, name of the dataset, dollar sign, name of the variable within the dataset. And the same is true for the Y. Same dataset, dollar sign, different variable name. We also want to apply the correlation methodology. So to do that, it's core.test is the function. Again, this is our data set in each instance, and we're telling R with this function core.test for our first variable, it's variable X, dataset name is dataset, variable $ is X, dataset name is dataset $ variable Y. These have to be equal sizes for correlation. And then in addition to that, we also want to create a graphical visualization. That's why we initiated these libraries, ggpubr and tseries, as our first bit of code. So with these libraries initiated, we can use the function ggscatter. So ggscatter is our function. This is the name of whatever the data set is. In our case, it's data set. If it were pencil, it'd be pencil. If it was fishbowl, it'd be fishbowl. If it was data set A, it'd be data set A. X is going to equal your X variable. So X equals X because it's the name of our variable in this case. If this was variable 1, X would equal variable 1. If it was variable A, X equals variable A. For Y, it's equaling Y because our variable name is Y in the data set. If this was variable B, it'd be Y equals variable B. If this was variable 2, it'd be Y equals variable 2. Okay? And down here, xlab equals x-axis and ylab equals y-axis. These are just the labels you're going to use for each axis, both x and y. You can set those to whatever you feel to be appropriate for your research. Here's the code again. You can find this in the video description below. If we run all of this code, our output should resemble the following. And again, you don't need R Commander to do this. You can do this in R or RStudio. The mean for our X variable is 4.8, standard deviation for X variable 3.79. Mean for our variable Y in the data set is 79. Standard deviation for our Y variable in the data set is 14.3527. Here's our t-score, degrees of freedom, p-value, and our correlation value. So here's one way of visualizing where everything is going to go in our APA format. You can pause the video here and use this, or have a cleaner depiction on the subsequent slide that we're also going to look at. So here are all the values. There was a positive correlation between the two variables, X and Y. Each had 10 observations. You don't necessarily need to have the number of observations. It's, as you can see, it's kind of extraneous because each is going to be equal in any case, but you can have them if you like. But as far as the APA format is concerned, you need to have whether or not it was a positive or negative correlation. The strength of the correlation you could place also if you see fit. Here is the values for our X value, our X variable. Mean equals 4.80. Standard deviation, we're using two significant figures, is 3.79. Y, our mean is 79. Our standard deviation is 14.35. Conditions T is 8. Degrees of freedom is there. Okay. Here is our T value, two significant figures, 0.37. P-value is 0.72. That's right here, two significant figures. And our Pearson product moment correlation coefficient is down here. We're going to go two significant figures. That's 0.13. So as you can see, there was a small positive correlation between the two variables. And when we take a look at the graphic that was created as a result of our code for such, we can see that small correlation illustrated. Here's the value of each variable, the corresponding value for X and Y in each instance. Here is our Pearson product moment coefficient, Pearson product moment correlation coefficient value right here. And here is our p-value to the right of that. Now, how will we interpret these results after we've reported them in case we're asked by our committee or our thesis advisor, how will we how would we actually break down in plain English what happened here? Well, the p-value, which is 0.72, that's indicating whether or not there was a significant correlation determined, while the Pearson product moment correlation coefficient, that's R equals 0.13, indicates the strength of the model, or the strength of association, as it were. The p-value is going to tell you whether the observation relationship, R equals 0.13, is unlikely or likely to have happened by chance. In this case, our p-value is 0.72, so this relationship is probably likely to have happened by chance. The R value is measuring the strength and direction of the relationship of the two variables. So really, this model isn't all that great. This relationship isn't all that great. We see that there is a small positive correlation, but because our p-value is not below an alpha value of 0.05, we couldn't really state that this was really a worthwhile correlation between the two variables. And as far as the Pearson product moment coefficient correlation is concerned, well, it's 0.13, so the strength of the relationship isn't even all that great. So not only can we say that, it wasn't statistically significant at a alpha value of 0.05, but the relationship, as far as the correlation is concerned, is also weak. And because, again, the p-value is above 0.05, this relationship actually might just be by chance. So we don't really have all that much here as far as relationship is concerned. Ideally, we would like this value here to be below 0.05, and ideally we would prefer this value here to be either above 0.5 or below negative 0.5. If you have both, that's ideal. But if you have one or the other, that could also be a indicator of decent results, meaning that the relationship is strong, though it might be by chance, or you can say for certain whether the relationship is strong one way or the other, whether or not the it was chance or otherwise as determined by the P. Here is our relationship as weighed against some of the examples from the prior slides. And those particular diagrams and the associated table demonstrating the strength of association were taken from this website here, which might also provide useful reading. I'll put the link in the video description. It might provide useful reading if you wanted to have more information as it pertains both to the p-value and the correlation coefficient value for a model. So that is it for this video. Thank you for sticking around. I hope that this was able to assist you with your research or your course. If you were able to take anything away from this, please consider liking and subscribing, and all the best of luck as you pursue your research endeavors. Take care.